In this video, we'll briefly discuss the basicity of aldehydes and ketones. So let's remember something that was mentioned in an earlier video. In a aldehyde and ketone, we have that carbonyl. The oxygen in the carbonyl is more electronegative than carbon. So the oxygen pulls electron density away from the carbon atom. This can be described as both an electron-rich area, so where the oxygen is an electron-rich area, and then where we have the carbon with electron density being pulled away from the carbon by the oxygen, we have an electron deficient area. All right, so if we have an electron-rich area, that oxygen has non-bonding electrons. Remember that a base is a molecule or atom in a molecule that uses non-bonding electrons to create a bond to a hydrogen. So if we have an acid around, here we just have a generic Bronsted-Lowry acid. A represents the acid molecule, and then H is the acidic proton in the molecule. Well, then that oxygen in the carbonyl from an aldehyde or a ketone can create a new bond to that proton from the acid, so long as the acid is strong enough to protonate an aldehyde or a ketone. So let's look at what happens, and we'll look at a specific example. We'll start with acetone. We'll use hydronium, H3O+, or emphasizing that hydrogen to oxygen bond. Aldehydes and ketones are basic at the carbonyl oxygen, so the electrons there can create a new bond to the proton. We do a proton transfer reaction, a reversible reaction, where now we have a protonated oxygen. One set of the oxygen lone pairs is now present in the bond to the hydrogen. It now has a +1 formal charge, and we have our H2O as a byproduct. Now, when we form this product, we have a protonated oxygen, positively charged oxygen. We can shift the location of the positive charge through resonance, where we can say that in another resonance structure, the oxygen atom owns the electrons in the pi bond. So now we're doing resonance here. Let's draw what this resonance structure looks like. We talked about this a lot in the previous unit, where any charges that are delocalized are more stable than a localized charge. So if we resonate the pi bond electrons between carbon and oxygen up to the oxygen atom, the oxygen now has 2 bonds and 2 sets of lone pairs, so it has a neutral charge, and the positive charge is now on that carbonyl carbon. This is a relatively common or relatively stable resonance structure because oxygen is more electronegative than carbon, so the positive charge being on carbon is stable. However, it's not as significant of a resonance contributor than the first one, because in the first one, all atoms have a closed shell. So here, all atoms have a full octet, or in other words, a closed valence shell. This on the right is the carbocation structure. So you may be wondering, why do we even show the carbocation structure if the first one that we drew is the more stable one, the more significant resonance contributor? Well, when we're thinking about resonance, this can help us understand the bonding or the reactivity of these molecules. So showing that a valid resonance structure has a positive charge on the carbon indicates that that carbon is even more electron deficient than before it was protonated, before the molecule was protonated. So it helps us understand overall properties of the molecule. Remember that the actual molecule that exists in nature is a hybrid of all of the resonance structures. So we can show the different resonance structures to understand properties of the molecule. Now, this first structure that we drew, let's write a little note down here. This is at a lower energy. So it contributes more to the resonance hybrid, or what exists in nature, the real molecule. Okay, so we use resonance to understand the properties of this molecule. This also helps us understand the relative acidity here. Usually oxygen, when it has a positive charge and it has a hydrogen bonded to it, that's a pretty strong acid. Well, the pKa of this molecule, after being protonated, is approximately -7. So this is a pretty strong acid. So that tells us that aldehydes and ketones are weak bases. Or let's say weakly basic. So the key takeaway here from this video is that aldehydes and ketones are weakly basic at the carbonyl oxygen. So long as a strong enough acid is present in solution, then some of the acetone or some of the aldehyde or ketone molecules will be protonated in solution.